All right, so in the previous video, we were looking at um, the concentration unit known as molarity and how we can use that to determine different pieces of information about a solution depending upon what we already know. What we're going to start to look at now is related to the concentration, but we're thinking about preparing a solution. So one way we can make a solution, we kind of saw some of the questions related to that in the previous section, is figuring out how much solution we need. So what volume do we want, as well as what concentration do we want. And then with those two pieces of information, we can figure out how many moles of the solute we're going to need, ultimately convert that to grams, and then just figure out how much of that do we need to weigh out to make the proper solution. But another way we can make solutions is via dilution. And essentially what this is just using a higher concentration solution and essentially just sort of watering it down. Doesn't necessarily have to be water depending on what the solvent is, but essentially just adding extra solvent to lower the concentration of that solution. So you can see an example here. So based on the color of these two solutions, they might be some sort of copper solution, maybe just based on the color. But because the one on the left is darker, that's going to be a higher concentration solution. So if we want to make a lower concentration solution, what we can do is transfer some of this to a separate container and then just add a certain amount of water. By doing that, we'll transfer the solution. When we're just transferring it, we still have the exact same concentration because the moles of solute are dispersed evenly throughout the solution because it's homogeneous. So we'll wind up with a smaller volume. We'll wind up with less moles initially in that other container. But because those are going to be related, they'll still be in the same ratio, we'll still have the same concentration. But let's say we maybe add 10 milliliters of that solution. But then we add enough water to bring it up to 80 milliliters total now. So because we're increasing the volume, while not changing the number of moles, we're decreasing the concentration. So this is just going to be the dilution process. And the example they use here is just thinking about if you add ice to your iced tea or whatever beverage you're drinking. As that ice starts to melt, it's going to increase, if we think about not drinking any of the drink as this occurs. But as the water melts, it's going to increase the volume of that solution now. But it's not going to change anything about the amount of tea or whatever the beverage is. So it's just going to become watered down. It's going to become diluted. And then with this, we've got a term known as stock solution. So we just consider that to be kind of the original, the already prepared, the higher concentration solution. And the reason it's just called a stock solution is because we keep it stocked. So it's already ready. It's in the chemical stock room, ready to go. But when we do this, we're going to measure out a known quantity of this stock solution. And then we're going to add a specific amount of solvent in order to get it to whatever the desired concentration is going to be. And one way or one area that this is important, or one area where this occurs, is going to be in pesticide application. So with the pesticides themselves, the pesticide active ingredient that you buy, if you were to apply pesticides, is a very high concentration of whatever that chemical is going to be. There might be a few other things mixed in to kind of help it spread on the plant better or stick on the plant longer, whatever it may be. But it's going to be primarily that active ingredient. And it's going to be at a really high concentration in the container that it originally comes in. So then when a farmer, whoever goes to apply that pesticide, they then essentially just take a small amount of the original pesticide and then just add it to a whole bunch of water. And then that's what gets sprayed on the crops or the field, whatever it is. So in that case, they're diluting the pesticide to get it to the concentration that they actually need. Because if they applied it just directly from the container, that would be a extremely high concentration. That would have way too much of the active ingredient in it. So there'd be a lot of negative effects in that case. Excuse me. Okay. And then with this, we can think about this mathematically. So if we think about the molarity equation, moles over liters, we can rearrange that to solve for moles. So it's just the molarity times the volume in liters. Because remember, molarity is moles over liters. So if we multiply it by liters, liters cancels and we're just left with moles, which is what we're representing with the lowercase n. And that'll be true for any solution we have. So what we can do is think about that for the first solution, so the stock solution. So N1, just the number of moles, molarity of that stock solution, and then the volume of that stock solution we're going to use. And then N2, or equation 2 here, we can think about that as the solution that we're preparing. So N2, the number of moles in that solution, the concentration in molarity of that solution, and then the volume in liters for that solution. But with this dilution process, if we just think about what's actually happening there, we're taking a small amount of that original solution and transferring it to a new container. So M1 is just going to be the stock concentration. L1 is just going to be the amount that we actually use of that original solution. So just beware if we have a question. In some cases, it may tell us that we have 500 milliliters of that stock solution available. But the value we're plugging in here is how much of it do we actually transfer. So we just want to be careful. We want to think about what information we're using here. But this is just going to be the volume of that stock solution that we use. And then what's occurring with the dilution is then we're just adding water to that stock solution. So we're increasing the volume, L2, while decreasing the molarity, M2. But because we're not actually changing anything about the number of moles of solute in that solution, what we actually have is N1 and N2 being equal. They're not changing at all. So what we can do is take the rest of these equations and put them together. So if N1 is equal to N2, that means M1 L1 is equal to M2 L2. And this is just going to be known as our dilution equation. And in this case, it's showing molarity and liters specifically. But with this equation, as long as we have the same thing on both sides, so we're going to see a couple different concentration units. So as long as the concentration units match on the left versus the right, they're going to cancel out. And then the same thing with the volume. So we could have liters, we could have milliliters, we could have any other volume unit, but as long as it's the same thing on each side, it doesn't actually matter what it is. And that's why it might be more useful to use this equation, C1V1 is equal to C2V2, because in this case, it's just saying concentration, 1 versus 2, in whatever unit, just needs to be the same. And then the same thing with volume, 1 and 2. Could be milliliters, could be liters, we could even use gallons or whatever for this equation. But as long as we have the same units on the left and the right for concentration and volume, it doesn't actually matter what units they are. But if we're just calculating molarity, remember that's where we always need to have moles over liters. But for this dilution equation, since the left versus the right are the same thing, the units are just going to cancel, so it doesn't actually matter what we have there, as long as they match. So looking at that dilution equation, if we have 0.850 liters of a 5 molar solution of copper, this would actually be copper 2 nitrate, and it's diluted to a volume of 1.80 liters by the addition of water, we want to figure out what the molarity of the diluted solution is. So remember, diluted means lower concentration. So we're trying to find the concentration of the new solution. So if we're thinking about C1V1 is equal to C2V2, in this case, we're going to be solving for C2. So what you can always do with a question like this is think about what information do we have and just label it. So 0.850 liters, 5.00 molar, that's going to be V1 and C1. And then we know how much we're diluting it to, so we know V2. So the piece we're going to be solving for then is just going to be C2. And what we can do is take our dilution equation, C1V1 is equal to C2V2, and just rearrange it to solve for that missing piece. And with a question like this, I would recommend kind of, if maybe not necessarily labeling if you don't feel like you need to, but just taking a moment to think about what each of these values represent, because we can solve for any piece of that dilution equation as long as we have the other three. But like I said, since we're solving for C2, we can just rearrange this to isolate C2. So we'll divide both sides by V2 to get C2 by itself. And then we have the other three pieces of information. We just need to plug them in. So initially we had a 5 molar solution that was 0.850 liters. So that'll be our top piece here. We're diluting it to a volume of 1.80 liters. So we can just plug all that in, do the math, and then all three of those values had 3 sig figs. So our final answer is going to have 3 sig figs. And then with this, also just think about if your answer makes sense. So in this case, we're taking a 5 molar solution and just adding a bunch of water to it. So our concentration should decrease. So something like 2.38 or 2.36 molar, excuse me, makes sense. If we wound up getting a higher molarity than 5, it likely just means that we switched up those volumes. So always just, again, think about where your answer should be roughly, just so you can see after you do that calculation if it's a reasonable value or not. And then with this one, our unit is just molar, just because that was the concentration unit we had for the other side of that equation. If we had a different concentration unit, we could still go about this the exact same way. We would just have a different concentration unit on our answer. So with the next one, what concentration of the solution that results from diluting 25 milliliters of a 2.04 molar solution of methanol to 500 milliliters? So again, we're taking a known solution, just dumping in a whole bunch of water. So we're going to see the concentration is going to decrease. And in this case, we're diluting it by about a factor of 20. So we should see the concentration be about 1/20th of the original. So about 0.1 is a reasonable answer for this one. But again, we can just go about rearranging our dilution equation. In this case, I put M1 just because we have molarity, but it could just be C1 and be the exact same equation, C2. But we've got the initial pieces up top, and then note, in this case, I just kept it as milliliters, just because as long as it's the same thing for both of those volumes, they're going to cancel each other out. So milliliters cancel. The only unit we have left here is molar. That's why we've got that as our final unit. And then, like I said, we're diluting by a factor of 20. So our concentration should be about 1/20th of the original, should be about 0.1. So getting 0.102 is a pretty good indicator that we've plugged everything in correctly. And then again, 3 sig figs in the final answer, because even though we have 4 sig figs in this second volume, 500.0, we only had 3 in the molarity, we only had 3 in that initial volume. And then since we're doing division and multiplication, we just match whatever value had the fewest sig figs overall. So it'd be the 3 from those top 2 values there. Okay. And in this case, we want to figure out what volume of a 0.12 molar hydrobromic acid solution can be prepared from 11 milliliters or 0.011 liters of 0.45 molar hydrobromic acid. So in this case, we're actually solving for V2, because if we look at these concentrations, 0.12 less than 0.45. So this is going to be the solution that we're making. This is going to be the solution that we're starting with. And in this case, we know V1, and it doesn't matter which of these values we use. It's just whichever one we use, that unit's going to match our second volume. So I'm going to use 11 milliliters. If you use 0.011 liters, you'd get ultimately the same value. We would just have it expressed in liters, so it would be a smaller number. But just like the previous one, we can rearrange that dilution equation to solve for the piece that we're looking for. So in this case, the second volume. And when we just plug everything in, we'll get 41.25 as our calculator answer. But we've only got 2 sig figs in all of these initial values. So we can only have 2 sig figs in our final answer. So we'll have either 41 milliliters, or if you plugged in 0.011 liters, you would just get 0.041 liters. Again, same exact value, just expressed it with the different units, or just moving that decimal over 3, essentially. And then an laboratory experiment calls for 0.125 molar nitric acid. What volume of 0.125 molar nitric acid can be prepared from 0.250 liters of 1.88 molar nitric acid? So again, in this case, we're looking for V2, because we've got M2, we've got M1, we've got V1. So we can just rearrange the equation in that same way. And then when we plug this one in, what we're going to see is that the volume is going to be 3.76 liters. So I think that's right around 1 gallon. I think 1 gallon's 3.785. But with this one, we can think about it. Because even though these are different units, if we think about it left versus right, M1 V1 is equal to M2 V2. 0.125 is half of 0.250. So the other value on that side of the equation has to then be twice what 1.88 is, just to make sure that it's balanced if we think about the original dilution equation. So just M1 V1 is equal to M2 V2 rather than the rearranged one. And then 3.76 is exactly 1.88. So again, we can be confident that we plugged everything in correctly there. And the volume going up a whole bunch, because we're taking this higher concentration solution and diluting it down to 0.125, and then that's a factor of, what is that, like 16? 1.88 divided by 0.125, 15. So we're diluting it by a factor of 15, so the volume here should go up by about 15, and that's exactly what we see, because 16 would be 4 liters. All right, so in this case, we would actually be thinking about this as if we're preparing the solution ourselves, so the diluted solution. So we might have 1.59 molar potassium hydroxide as the stock solution in the lab, and then we want to make 5 liters of a 0.1 molar solution of potassium hydroxide. So we need to figure out how much of that stock solution do we actually need. So in this case, we're looking for V1. Because if we were actually making this 0.1 molar potassium hydroxide, we would measure out the potassium hydroxide from the stock solution that we would need, and then we would just add enough water to bring it up to 5 liters. Now, though, with the base, we might want to add the water first, and then add the small amount of potassium hydroxide second. But with this one, we've got M2 with the 0.100 molar. We've got V2 with the 5 liters, and then we've got M1 with the 1.59 molar. So again, if we wanted to, we can always label what these things are. So this will be C1, this will be V2, this will be C2. So the only piece we're missing then is V1. So we're going to rearrange that dilution equation to solve for V1. Whoops. So we'll have C2 times V2 over C1. So C2 times V2 over C1. And let me get rid of this writing. And then when we plug all that in, we'll get 0.314 liters. So again, 3 sig figs in these initial values, 3 sig figs in our final answer there. And then again, thinking about if this one makes sense, 0.314 liters, we've got a higher concentration of that stock solution. So we're going to need a smaller amount than we'll have in the diluted solution overall. So 0.314 makes sense. And then again, we're diluting this one by a factor of almost 16. So it makes sense that the volume here is about 1/16 of the second volume. And then with the bottom one here, what volume of a 5.575 molar solution of glucose can be prepared from 50 milliliters of a 3 molar glucose solution? So again, we're doing kind of the same thing. Actually, in this case, we're solving for V2 because we're thinking about 0.575 as the M2. We're thinking about 3 molar as M1 and the 50 milliliters of that solution as V1. So we've got to solve for V2 in this case. And then when we do that, we'll get 261 milliliters. So in this case, since we were given 50 milliliters, I just, again, kept that as the unit, just knowing that that's going to then have to be the unit on our answer here. And since this question doesn't specify milliliters or liters, I would just keep it in whatever unit you're given for the other one. Just save yourself one step, one potential area where you could sort of mess up that conversion. But if you did have it in liters, you'd have 0.05000 liters, and then you would get 0.261 liters. And again, same exact value, just using a different unit to express it. All right. So looking at a couple other units we have here, one of them is going to be mass percent. And essentially what this is very similar to the percent composition that we looked at in one of the earlier sections of this chapter. But where percent composition was the mass of the element over the mass of the compound, what we're looking at now is just the mass of whatever component in that solution that we have divided by the mass of the entire solution. And a lot of products tend to have labels like this. So sometimes you'll see mass percent, percent mass, percent weight, W over W percent, so weight by weight. There's a couple different ways to express it, but they're all referring to the same idea. So just how much of the solution by mass is whatever that component. And one common example of this is just going to be bleach. So the active ingredient in bleach, sodium hypochlorite, NaOCl. The solution of bleach is going to be 7.4% sodium hypochlorite. So if we had 100 grams of that bleach solution, 7.4 grams of that solution would be the sodium hypochlorite. So with this one, a 5-gram sample of spinal fluid contains 3.75 milligrams of glucose. What is the percent by mass of glucose in the spinal fluid? So again, we're just going to do the mass of that component. So in this case, the glucose divided by the mass of the entire solution. So in this case, the 5-gram sample. But with it, we just need to make sure that those units match up. It doesn't actually matter what they are. As long as they're the same, they'll cancel. So that when we multiply by 100, we just wind up with a percentage. So with this one, since we've got 5 grams, we just want to make sure that we use the glucose value in grams rather than 3.75 milligrams. In that case, we wouldn't have the units match up, so they wouldn't cancel. But in this case, we'll just have 0.00375 grams divided by 5 grams, and then multiply by 100 to make it a percentage. So in this case, it's showing the conversion from milligrams to grams, just in case we weren't given that value. But what that's going to give us then is a 0.075% glucose solution. And then we've got concentrated hydrochloric acid is an aqueous solution of 37.2% hydrochloric acid, HCl, that is commonly used as a laboratory reagent. The density of this solution is 1.19 grams per milliliter. What mass of hydrochloric acid is contained in 0.500 liters of the solution? So in this case, we know if we had 100 grams of solution, we know 37.2 grams of that would be hydrochloric acid. But we don't know the mass of this solution. We've got the volume. But since we're also supplied with the density, we can determine the mass of that solution by multiplying those. We'll have to do a little bit of a conversion to get the units to match up. But then once we get the mass of that solution, we can then use the percentage to figure out exactly how many grams of hydrochloric acid we would have. So the first thing we need to do is convert that 0.500 liters into milliliters. So we're just going to wind up with 500 milliliters then. So again, just multiplying by 1,000, 500 milliliters. And then we can use the density, 1.19 grams per milliliter. We multiply those together. Milliliters will cancel. We'll just be left with grams of that solution. And then using the percentage, we can then figure out of that many grams, how many of them are going to be HCl. So again, once we do that conversion to get milliliters, we've got the density. So 1 milliliter of the solution weighs 1.19 grams. So milliliters is going to cancel. Now we're just left with grams of that solution. And then based on the percentage, 37.2%, that means for every 100 grams of solution, 37.2 of them are going to be hydrochloric acid. We could have also done 10 grams of solution here, 3.72 grams of hydrochloric acid. It's just if we do it 100, we can just use that percentage as the number of grams directly, similar to some of the empirical formula questions we were looking at earlier in the chapter. But again, if we just use these units, milliliters cancels, grams cancel, we're just left with grams of HCl. We can kind of use the units to help guide us where we need to go. And then with this one, we've got 3 sig figs, 221, because in the initial question, 37.2%, 1.19 grams per milliliter, 0.500 liters, all have 3 sig figs. So with the second one here, we want to figure out now what volume of concentrated hydrochloric acid contains 125 grams of HCl. So in this case, we're kind of going in the opposite direction. So see if you can set that one up. You just want to pause the video because I'm just going to kind of start to go through it. But like I said, it's just going to be kind of the reverse. In this case, for the first one, we went from volume to grams of HCl. Now we're going from grams of HCl to the volume of that concentrated hydrochloric acid. So we'll start with 125 grams, and then since we're going in reverse, we'll have to essentially flip these parentheses. So we'll have grams of HCl on the bottom, grams of solution on top, and then we'll have to do the same thing with the density after that. But again, if we look at the units, grams of HCl canceled. So for every 37.2 grams of HCl, we have 100 grams total of solution. And then because 1.19 grams of that solution is equal to 1 milliliter of solution, we can figure out what the volume of that solution would be. And then again, we've got 3 sig figs, just because we had 3 sig figs in the values we were given to use. All right. Another unit, very, very similar. So in this case, it's exactly the same, but instead of being focused on the mass component of the solute in the solution as a whole, we're just focused on the volume. So what volume of the solute, what volume of the overall solution. So we've got percent volume or volume by volume percent, just because again, we'll have by 100% at the end. And with it, alcohol ABV, alcohol by volume, is a similar calculation. So of the total solution, so of the beverage, so like 12 ounces for a beer, whatever it may be, what percent or how much of that volume is alcohol, and then just multiply it by 100 to get a percentage. So if we look at an example here, rubbing alcohol, which is isopropanol. So drinking alcohol is ethanol. There's a whole bunch of other alcohols though, that are primarily used for cleaning and chemical reactions and solvents and things like that. But isopropanol is usually sold as a 70% volume aqueous solution. If the density of isopropyl alcohol is 0.785 grams per milliliter, and I just noticed that the textbook uses 2 different names for the exact same thing. So isopropanol isopropyl alcohol and rubbing alcohol are all the same thing. But if the density of that solution is 0.785 grams per milliliter, we want to figure out how many grams of isopropyl alcohol are present in 355 milliliters of rubbing alcohol. And just like the previous one, we're going to be able to use this percentage as a conversion factor, because 70% by volume really means that for every 100 milliliters of solution, we've got 70 milliliters that are going to be the isopropanol in this case. So if we want to get to grams, we got the original volume of the solution. We can use this percentage to figure out the volume of just the alcohol. And then once we have the volume of the alcohol, we can use the density to convert that into the mass. We can get the grams of isopropyl alcohol that way. So with this one, 355 milliliters of solution, but for every 100 milliliters of solution, we've got 70 milliliters of isopropyl alcohol, just because it's a 70% by volume solution. And then because we have the density, every 1 milliliter of that alcohol weighs 0.785 grams. So just going through milliliters of solution canceled, milliliters of isopropyl alcohol canceled, we're just left with grams of isopropyl alcohol in that case. And then with the next one, kind of the same idea. So wine is approximately 12% ethanol by volume. Ethanol has the molar mass of 46.06 grams per mole and a density of 0.789 grams per milliliter. We want to figure out how many moles of ethanol are present in the 750 milliliter bottle of wine. So in this case, it's going to be a very similar calculation. But essentially, we're going to have to go one step further because we don't want to just stop at grams. We want to, in this case, convert to moles of ethanol. But those first few steps are going to be exactly the same. And then we'll just use the molar mass at the end to make that final conversion. So we'll start with 750 milliliters of wine. We'll use the 12%. So it'll be the same thing here. It's just we'll have 12 milliliters of ethanol on top. Then we can use the density of ethanol to convert it to grams. And then we can use the molar mass to convert from grams to moles. So again, 750 milliliters of wine. For every 100 milliliters of wine, we're going to have 12 milliliters of ethanol, just because it's a 12% by volume solution. And then based on the density, for every 1 milliliter of ethanol, there's going to be 0.789 grams of ethanol. So this would give us how many grams of ethanol we have in this bottle of wine, but we want to go to moles in this case. So now we're just going to use that molar mass. We had grams on top here. So we're going to have the grams on the bottom for the molar mass, moles on top, and ultimately that's going to give us 1.5 moles. And then for this one, we've got 2 sig figs because 12% has 2 sig figs, 750 has 2 sig figs as well. So we're just going to round to the 2 sig figs with 1.5. Okay, and then there's also, so if we kind of take those two together, we had mass percentage, we had volume percentage. So we can have a mixed percentage here, where it's the mass of the solute and the volume of solution. And this has certain applications, particularly in sort of medical fields. So with saline solutions, so if you've ever gotten an IV, you may have had a salt solution, and that's a 0.9% mass by volume solution. So there's 0.9 grams of the salt for every 100 milliliters of solution. And then if you've ever had your blood sugar tested, so diabetics have to do it quite often, but if you've ever had your blood sugar tested, what that's going to be is the calculation of sugar in milligrams per deciliter of blood. So again, it's going to be a mass of solute over volume of solution. Same thing with the salt solution here, or the saline solution, I should say. So these are going to be different concentration units that'll be used in certain applications, like I said. medicinal fields tend to have these quite often. And then another common unit is going to be either parts per million, so ppm, or parts per billion, ppb. And essentially they're the same idea as the percentage. It's just instead of thinking about it as 100, now we're just going to have it kind of out of a million or a billion. So it's just going to be the mass of whatever the solute of interest is, divided by the mass of the entire solution. And then for parts per million, we just multiply it by a million. Parts per billion, we multiply it by a billion, so 10 to the 9th or 10 to the 6th. And then the units with these ones are just the symbol themselves. So ppm, so we could have 15 parts per million, or ppb, 15 million or 15,000 parts per billion. But essentially, that's just telling us if we had a million pieces, how many of them would be that solute, or if we had a billion pieces, how many of them would be that solute. And with these units, they're extremely common environmentally. So with the EPA, for instance, they monitor different contaminants in soil, air, water, whatever it may be, to make sure that the soil that we're growing our crops in, or the soil that we're living around, the air that we're breathing, the water that we're drinking, the water that we're using to grow crops, to make sure all of that's safe for human consumption. They monitor the concentration of different contaminants. And a lot of the times the units they'll use to express the thresholds, as well as the actual concentrations, is parts per million or parts per billion, depending on what that substance is. And like I said, tap water is going to be something that is monitored closely for different contaminants, since we drink so much of it. And then one thing you can do to reduce the amount of contaminants is just use a water filter. So sometimes you'll have one that's just straight through the fridge. I have one of the Brita filter things that you fill up and put in the fridge. But using anything like that would help collect any contaminants. But the EPA, the different water agencies, do monitor the concentrations very closely. So with this one, if we're thinking about those types of calculations, according to the EPA, when the concentration of lead in tap water reaches 15 parts per billion, certain remedial actions must be taken. So with the EPA, they're not monitoring to make sure that there's no contaminants. They've done calculations to determine what a realistic threshold is, and their threshold is that there won't be adverse effects except for one person in a million. So if 1 out of a million people get sick from that exposure, they consider that to be acceptable risk. Just because because it costs more money to reduce that risk even further. So that's kind of the balance they've struck between safety and economics, essentially. But in the case of lead, if we get above 15 parts per billion, so if we had a billion things, essentially 15 of them are lead, that water is no longer safe to drink. We want to think about what is the concentration in parts per million, so converting parts per billion to parts per million, and then also at this concentration, what mass of lead would be contained in a typical glass of water, so 300 milliliters total. How much lead would be in that sample? And then with this unit here, this is just going to be microgram. So 1 microgram is 1 millionth of a gram. Okay. But with the first one, if we're trying to figure out what the parts per million would be from that parts per billion concentration, thinking about those equations, they're exactly the same. It's just parts per million is 10 to the 6th, parts per billion is 10 to the 9th. So they're just going to be different by a factor of 3. And in this case, we're going from parts per billion to parts per million, so B to M. So in this case, we're going to have 10 to the 3rd less particles, essentially less things. So we should have 10 to the 3rd fewer in terms of our value. So we're essentially just dividing by 1,000 here. We're moving that decimal over 3. And that's why it goes from 15 just to 0.015 parts per million. And then with that conversion, 1 part per million is just equal to 1,000 parts per billion. Because a billion is a larger number, we should have more parts of whatever that substance is, in this case lead, if we're looking at a billion, than we would with a million. So it's essentially just scaling up the unit or scaling it down, depending on which direction we're going, which is what we're doing here. And then for the second one, at this concentration, what mass of lead would be contained in a typical glass of water? So we're going to be able to use dimensional analysis for this one. We've got to make a couple of assumptions. So first, we're just going to assume that the density of water is 1 gram per milliliter. It's pretty much exactly that, depending on the temperature. It does change slightly, so sometimes it's like 0.998 grams per milliliter or whatever it may be, but we're just going to assume 1 gram per milliliter. So by doing that, then we can determine the mass of this solution. So we'd have 300 grams of water in this glass then. And then if we just think about what parts per billion is, 10 to the 9th is billion. So if we had 15 parts per billion, that means if we had a billion grams, 15 of them would be lead. So we can do this calculation to figure out how many grams of lead we would have. But this question in particular specifies micrograms. So we've got to go one step further. We've then got to convert that grams to microgram. And since a microgram is 1/1,000,000th of a gram, that means we would have a million micrograms in 1 gram. Conversely, you could have 1 microgram over 10 to the -6th grams. We do the same thing. I just like to keep it with the positive exponent, so that's why I have it like this. But now we're just going to be moving that decimal over 6. So in this case, essentially times 10 to the -6th cancels out 10 to the +6th. So we just wind up with 4.5 micrograms. So if the concentration of lead was 15 parts per billion, and we had a regularly sized glass of water with that concentration, there'd be 4.5 micrograms of lead. And similarly, a 50-gram sample of industrial wastewater was determined to contain 0.48 milligrams of mercury. We want to express the concentration of mercury in parts per million and parts per billion for that sample. And with this one, it's probably a little bit easier than the other one, because we can just think about what the parts per million or parts per billion equation is. And it's actually going to be exactly the same. It's just going to be what number do we multiply at the end by, either a million 10 to the 6th or a billion 10 to the 9th. But we've got the mass that's coming from mercury. We've got the mass of the entire sample. So in each case, we'll just start by doing 0.48 milligrams divided by 50 grams. But again, we just have to make sure those units cancel. So we're going to convert one of these to the other. You could convert 50 grams to milligrams. You could convert 0.48 milligrams to grams. We just need to make sure that these units match. So what I did is just start with 0.48 milligrams over 50 grams, and then do that unit conversion. So 1,000 milligrams is equal to 1 gram. Milligrams will cancel. We'll just be left with grams on top, grams on the bottom. And that's the same way I'm starting the parts per billion, because it's the same sample. The only thing that's going to be different between these two is just what do we multiply at the end. We multiply by a million for parts per million. We multiply by a billion for parts per billion. And that's why we just got ppm versus ppb. And then again, thinking about it, parts per billion, 10 to the 9th, now has 1,000 times as many particles. So whatever the solute of interest is, in this case, the mercury, we should have 1,000 times as many of those particles as well. So that's why we're essentially, again, just moving that decimal over 3. 9.6 parts per million is the same as 9,600 parts per billion. And with each of these, we just got 2 sig figs, just because we had 2 sig figs in the amount of mercury. So we've got 3 in the sample overall, but only 2 in 0.48 milligrams there. So we can only have 2 sig figs in our final answers.